Hello, Ace Trick students. Mr. Meunier here again. Today, I want to talk about solving a system of polar equations. This will be our last lesson for this school year, our last lesson in this shortened unit on polar before we take a test later this week to kind of wrap up this semester and this school year. I hope everybody's doing well out there, and we'll try to make this as painless as possible. So we've been dealing with polar units for the last couple of weeks, and we've discussed how polar is an alternate way of plotting points. Instead of using our traditional grid system horizontally and vertically, we're going to use a circular system where we have a radius, that is the distance from the pole, the center, and then an angle, theta, which is the direction in which that point is at in relation to the polar axis. A polar system today is when we're just going to be doing multiple equations at the same time. So multiple equations at once. You solved systems of equations in algebra. You probably remember doing that by something called the substitution method or the elimination method. And we're going to kind of utilize those here today as well. Graphically in algebra, you could find the solution to a system of equations by finding the point of intersection. One nuance with polar is that the point of intersection where the curve crosses does not always align with a solution. So we're going to use the graphing calculator to look for potential solutions, or these are your intersection points. Okay. We're going to use algebra and trig to find the exact solutions. We're going to use some substitution and elimination method. And I, just for simplicity's sake and to keep our answers aligned, would like your solutions, the angles, to always be between 0 and 360 degrees. I want them in degree mode. And I want our radius to be greater than 0. I want to utilize a positive radius on these. And then last thing to say is intersection points do not have to match the solutions. Intersection points are not always solutions to the equation. Again, intersection points are not always solutions to a polar system, and that differs from your traditional rectangular systems where the intersection points were solutions to a system. I want to try to make this a little bit shorter. So I'm not going to do this first example. It was pretty straightforward. Let's skip into the second example here. So on example 2, we have a polar equation, r equals 8 cosine theta, and also r equals 5. First thing I want to do is graph each of these on the same polar curve and just make a sketch to find potential solutions, find these intersection points. So with my calculator or on Desmos, that's always a possibility that we went over last week. If you're using your calculator, make sure we put this in polar mode. So graph entry, polar. Your graph has to be in radian mode, by the way, for this to work. We have r equals 8 cosine of theta, I believe. Hit enter. And then if I hit tab, I can pull up another line and enter r equals 5. And we have a curve that looks somewhat like this. Looking at this, it becomes apparent that we probably have 2 intersection points. There's no tricks involved there. It looks like we have 1 intersection point in the first quadrant, a second intersection point in quadrant 4. I just want to make a simple sketch of this. We had one coming out like this, another one like this. 2 intersection points. Then we need to solve this to verify those intersections are solutions. Solving this is pretty straightforward. Since each of these equations equals r, equals the radius, we can set them equal to each other. So 8 cosine of theta equals 5. I want to isolate theta, divide the 8 over. So cosine theta is 5/8. And then move cosine by taking the inverse of this. And we go to our calculator and type in the inverse cosine of 5/8. Now for this to work, I have to be in degree mode. So I want my answer to be in degrees. Get the inverse cosine of 5/8. I put a decimal point after the 8 just because I want my answer to be in decimals. And again, I'm in degree mode up here because I want my answers to be in degrees. And we get about 51.3 degrees. We'll say round to the nearest tenth. Realize when we do an inverse function, our calculator only gives us one solution. It is up to us to figure out the other solution. So 51.3 is this angle in the first quadrant. We can use our reference angles to figure out the other solution. Cosine is a positive number because 5/8 is positive. Cosine is positive in the first quadrant and the fourth quadrant. And again, this other intersection point is in the fourth quadrant. So I know that this gap here is 51.3 degrees, just like this gap in the first quadrant is 51.3 degrees. Again, those are the reference angles. That's how far you are from the nearest x-axis. It's always a positive distance as well. If we're in the fourth quadrant, this is a 360-degree location. 360, take away the 51.3. So that's the first angle. Second angle is going to be 360 minus 51.3. Just make sure I don't mess up here. 360 minus 51.3 is 308.7. So the other solution based off of inverse cosine is 308.7 degrees. Those are our angles. We need to find the radius for these, and this one's a little bit easier because thankfully that second equation has a constant radius of 5. So for these to have a solution together, to intersect together, it has to be at that fifth ring. So R is 5. We have solutions at 5 comma 51.3 degrees and 5 comma 308.7 degrees. So our solutions are aligning with the points of intersection. That is typical. It just does not have to happen. But that is fairly typical. Okay, moving on. Oops. So now we got 6 plus 4 cosine theta and 5 plus 8 cosine theta. Same routine here. I want to make a sketch to find potential solutions and points of intersection. Something like that. I go to the calculator, 6 plus 4 cosine of theta. I'm going to go back to my graph. I want this to be in radians. Again, if I'm in graphs, I have to be radians, degrees, solve in degrees. I want to get rid of the curves I already have. Let's delete those things. Tab brings up a new window. We're going to do 6 plus 4 cosine of theta. There's the first curve. Tab, I can type in 5 plus 8 cosine of theta, or Desmos works for this as well. if you don't have a graphing calculator to work with. I'm going to zoom this one out a little bit, a little tight on the picture. All righty. Move these out of the way. And we're looking at this. These are a couple of limesons. If you remember from our labels last week, it looks like we're intersecting again in the first quadrant and the fourth quadrant. It does not have to be a first and a fourth quadrant for this to work. It's kind of happened that way because these have been cosine specific functions, and they're positive cosines at that, and cosines positive in the first and fourth quadrant. That's why this is happening. It's not a coincidence in that regard. It is a coincidence in that the examples have been similar cosine type problems. So sketch this thing out. We have, and again, it's a rough sketch. Something kind of like this. And something kind of like that. And again, we're looking at two intersections. Now let's find those or verify what are the solutions. So we have to solve this. And like we did last time, set these equal to each other. 6 plus 4 cosine of theta needs to equal 5 plus 8 cosine of theta. Let's move the 5 over to get the constant terms together. 1 plus 4 cosine of theta is 8 cosine. Let's move the cosines together. So subtract the 4 cosine to the right side. 1 equals 4 cosine of theta. Let's move that number 4 away from cosine. 1/4 is the cosine of theta. Let's move cosine by taking its inverse. So the inverse cosine of 1/4 equals theta. I know the calculator only gives me one answer always on an inverse trig function, but I do realize a positive cosine will have an answer in the first and the fourth quadrant. With the calculator, I'm going to put this back in degree mode, and I'm doing the inverse cosine of 1/4, and we get 75.5-ish degrees. Again, that's the answer here in the first quadrant. So I know this reference angle is 75.5. That tells me the other solution is 75.5 degrees away from the x-axis into quadrant 4. So the second angle is going to be 360 minus 75.5 degrees, which is going to give us, let me double check and make sure I don't make a silly mistake, 360 minus 75.5, 284.5. Okay. So we're in good shape on our angles. We have to figure out the radius this time. The radii, I should say. It's not a constant, so I can't assume it's just a single value. I need to take my angles and plug it into either of the originals. So radius 1 here would be 6 plus 4 cosine of 75.5 degrees. If I go to my calculator, we can work this out. 6 plus 4 cosine of 75.5. I'm in degree mode. We get about 7.0. And I really should try the second one. And again, just like in substitution elimination for X, Y problems, once you have answers, it doesn't matter which equation you plug back into. So either one of these will work. We go 6 plus 4 cosine of 284.5. We're going to get the same answer because of the nuance of this problem. Again, about roughly 7.0. So closing up here, we have solutions at 7.0 radius, 75.5 degree angle, and 7.0 radius, 284.5 degree angle. Just like the last one, both solutions corresponded with our points of intersection. This last one we're going to work on is not going to be that way. I just want to show you what can happen and why you have to kind of have a picture and some work on the side to make these go. So example 4 here, 5 sine of theta, 2 cosine of theta. Just like the other ones, let's make a sketch with our calculator. Notice there's no graph because I'm in degrees. You have to be in radians for these polar curves to work. I'm going to get rid of the ones we did the last time. Tab brings in new ones. Look at the question again, 5 sine and 2 cosine. So 5 sine of theta, whoops. It's like this, tab, 2 cosine of theta. Not theta pi, theta. All righty, I'm going to zoom this one in a little bit because we're a little bit far out. And I'm going to move these out of the way. And we're looking at this. A couple of circles this time. Oops. It looks like we're looking at 2 intersection points. One up in the first quadrant, another one appears to be at the pole. A little sketch. Okay. And again, 2 intersections. So let's find these things. Set the equations equal to each other. We're going to solve. This one's unusual in that we have different trig values. And that was never something we wanted to have. So to make this work, I'm going to divide the cosine piece over. Because if I have sine divided by cosine, hopefully you remember that turns into a tangent. So if I divide by cosine on both sides, cosine and cosine equals 1. So I have a 2. Sine over cosine makes this a tangent problem. Then move the 5. So tangent is 2/5. Take the inverse. And calculator. Remember, inverse, calculator only gives you one answer, but I know tangent is a positive number. Tangent's a positive 2/5 in the first quadrant. Tangent's also positive in the third quadrant. First quadrant kind of lines up with this intersection point. Third quadrant seems a little bit like a mystery, but we're going to roll with it. So inverse tangent of 2/5. Go back to a calculator. Put myself in degree mode. We're going to do inverse tangent 2/5. whoops, control enter, make it a decimal, about 21.8 degrees. So again, that means this is a 21.8 degree reference angle. I need a third quadrant answer of 21.8 because tangent's positive in the first and the third quadrant. So the axis here is 180. I want to go increase that by 21.8 degrees. So theta 2 is going to be 180 plus 21.8, which is 201.8. So I have angles of 21.8 and 201.8. I need to use those angles to figure out the radius. If I go and plug it back into the original, first radius is 5 sine 21.8 degrees. So calculator, 5 sine 21.8. We get about 1.9, I will say. And then I can do 5 sine 201.8. Oh, we got negative 1.9. So 1.9 and 21.8, that appears to be this, because when you're plotting points, we find the angle, a 21.8 degree angle is up here in the first quadrant, 1.9 units towards that puts you on this point of intersection. The other spot though, 201.8 degree angle, that's down here in the third quadrant. Negative radius, though, says to go away from it. So if I go away from that third quadrant, 1.9 units, it puts us on top of the solution we already found. So these are identical solutions. They're identical points. We only have one solution at 1.9, 21.8 degrees. Negative 1.9, 201.8 is the same spot. So what about the pole of 0, 0? That's just an intersection point. It's not a solution. And basically what happens is they're not coming together at the same moment. If you think of 0 degrees out here at 0, this sine problem, 5 sine of 0, the sine of 0 is 0, 5 times 0 is 0. So your sine, your blue curve, is sitting right here at the pole when this whole system begins, while the red problem, the cosine, well, cosine of 0 is 1, and 2 times 1 is 2. Cosine is out here on that purplish pink dot. They're not together at the same time. Then as the degrees start to tick off, this sine curve, this green dot, begins to work its way up this circle. And then the pinkish dot works around and they collide at this point. So really, polar systems give us more information. It tells you not only where do things cross, but it kind of tells you the moment when they impact in some ways. And that's what's happening here. At 21.8 degrees, or maybe 21.8 seconds, if you want to think of a time problem, they collide together simultaneously. Then they kind of continue on, and they both cross this spot at the pole. They don't do it at the same moment. So that's not a solution. It's simply an intersection point. You probably won't see that on a test or a quiz or anything, but it's a good thing to keep in the back of your head for a future course. That concludes this, what I wanted to go through today. Your assignment is a Schoology assignment. So complete and submit Schoology assignment. by 11 a.m. Wednesday. That'll be completion grade. Wednesday will be kind of get ready for a test. You'll have a test later this week covering polar, everything we've done since our vector test. And that concludes the year for the most part, guys. Don't hesitate to send me questions or concerns. I'm happy to answer any of those things. Only other thing we have to take care of is your textbook. Please, next week, Tuesday, Wednesday, Thursday, the 26th, 27th, and 28th of May, the school will be open from 9 a.m. to 6 p.m. Please return your book. Please write your name inside of the book. And that's about all we have to take care of. Hope you're all doing well. Again, send me any more questions that you might have, and good luck out there.